Now, we've talked about how to try to go about finding outliers with regard to our covariates and having high leverage. Now, we need to consider outliers in our outcome. And so, for a given combination of our covariates, we need to look for outliers in our outcome. And if we do find any such observations that have unusually large residuals, we're going to call those regression outliers. And let's say we've got two predictors. The mean structure, right, of constructing our regression is just a plane. And so we're looking for observations that fall exceptionally far from the plane compared to other observations. And the way that we're going to do this is by considering standardized residuals. And the reason that we're starting off with looking at the standardized residuals here is because, again, we're assuming that in expectation, the errors in our model have constant variance and are identically and independently distributed normally. Now, these estimated errors or the sample residuals do not in practice have equal variance. So what's going to happen is that observations with high leverage tend to have smaller residuals. Again, that's because they're pulling the regression closer to them, right? They're going to actually be closer to it because they're having such an impact on it. Again, this is an artifact of how we're fitting our model. These points can pull our fitted model closer to them, which is giving them a tendency toward having smaller residuals. So what we're going to do is we can form a standardized residual which allows them to have all equal variance. And that way we can determine, again, which observation is potentially having undue influence on our fitted model. So the standard error here of our residuals is going to be our estimate of sigma times the square root of 1 minus the hat value for each observation, which, in case you're curious, is equivalent to, again, remembering sigma, our estimate for that is the square root of our residual sum of squares over the number of observations minus the number of predictors minus 1, and again, times the square root of 1 minus the hat value. So a big issue with this is that the distribution of these errors isn't going to be a t-distribution because the numerator and the denominator are not independent. So we cannot use or reference a t-distribution for our test statistic here. So we're left with this little puzzle of what are we going to do? And our workaround for this is that we're going to estimate the standard deviation of the standard error for our estimates of the residuals with a sum of squares that doesn't include that observation's residual. So we're essentially going to delete the observation that we're looking at and refit the model based on that n minus 1 observations. And then we're going to get a sigma that doesn't have that observation calculated into it. And then this can give us the studentized residual. So now sigma in the denominator is not correlated with the numerator, and therefore we can reference the t-distribution for a test statistic. This is big because now we can get back into our null hypothesis testing and we can use the t-distribution to judge what's a large studentized residual, or again, kind of going back to our null hypothesis framework, we want to know how likely we are to get a studentized residual as far away from zero as the ones that we're getting if the null was true. This way, we can more concretely test for outliers by comparing each of these studentized residuals to a t-distribution, and here I'm just listing what the degrees of freedom are so you know. Now, usually we only have to be concerned about the largest studentized residual, so perhaps we need to take a closer look at those observations that have studentized residuals with like an absolute value over 2. Now, if we were going to go ahead and do this in R, it's really simple. We can just use the R student function. And again, with our LM object. And then I'm just sorting this to show you the largest ones. And again, these are the ones that are near absolute values of 2 that we may be more concerned about. And there's another way that we can get the studentized residuals, and we can just look at these quote adjusted p-values. Now, this Bonferroni correction is really multiplying the p-values by the number of residuals. So again, it's almost standardizing the way in which we're comparing our studentized residuals. So the way that we can do this in R is by using the outlier test, and again, just putting in our LM object. And again, what we can see is that we get the unadjusted p-value that is associated with referencing our t-distribution, and we can get the Bonferroni p-value. So what's important here is that if we just looked at the unadjusted p-values, we wouldn't necessarily think that any of our studentized residuals are greater than we would expect under the null. Now, if we look at the Bonferroni ones, we can see that there really actually isn't any p-value that is below 0.05. So this model doesn't necessarily have any extreme residuals.